Hello everyone, I am Alessandra Dolmeta, a PhD student of that department at Politecnico di Torino, and I'm part of the VLSI group under the supervision of Professor Guido Masera and Maurizio Martina. Today I will present you my thesis that is a post-quantum secure RISC-V application core for IoT, a PNRL research thesis developed in collaboration with Telsey Company. My research focuses on post-quantum cryptography and hardware design, so how to make our device secure in a world where quantum computer will be powerful enough to break today cryptography. I will show you how we are preparing for the moment where they become a threat, because we know that they will be able to destroy confidentiality and authenticity of today's digital communication system. The solution is exactly post-quantum cryptography. That is basically a set of algorithms that is built on very hard mathematical problems which are designed to resist to a quantum computer attack. There are already an ongoing standardization process that is led by NIST to decide which of these algorithms will become a new global standard. And now, if you think that it's too early to worry about this, well, government worldwide doesn't agree, because they are already leading the transition, aiming for full PQC adoption before 2030. So this is a really actual problem. The scope of my work, therefore, is clear. Post-quantum cryptography is mathematical secure, of course, but this is made of a computationally demanding function. And while mathematicians may enjoy this operation on paper, in practice they put an heavy load on software implementation. And so my research basically focuses on how to make this algorithm practical, especially on resource-constrained devices. Because if you try to run them on pure software on an IoT devices, it will run very slow, whereas optimized implementation can be completed in just some microseconds. And that is where my works come in. I designed hardware accelerator for RISC-V processor, and you may ask why RISC-V? We choose RISC-V because it's open, flexible, and customizable. It is, by definition, an open instruction set architecture which can be easily extended with your own instruction and your own accelerator. So it's like a modular toolkit. Instead of forcing every algorithm to run on the same generic CPU, we can adapt the CPU itself to the algorithm. There are different ways to integrate accelerator. The first one we have implemented were loosely coupled because it was a quite common approach. But in the first year, we discovered a new interface that is the XXXVIII interface, introduced in 2023 by the Open Hardware Group. And this is an interface that is designed to integrate a custom accelerator and coprocessor without modifying the CPU. So it is becoming so important because it allows direct access to the register file of the core using standard protocol and facilitating the integration approach. And my work has been actually one of the first systematic studies of this interface, exploring in depth how can the different accelerator be designed and tested with this new interface, comparing also it with older approach. So now I don't have the time to go into the details, but I want to show you some of my work, like Kronos, which is the most complete example in which I am working on Ketchak, that is basically the main bottleneck of all PQC algorithm. And what I have done in these 3 years was implementing different versions of Ketchak, test it and compare it on different platforms and within different projects like Serix and Tristan. And basically what we have tried to do is to starts with a Ketchak loosely version, which was implemented on Palpissimo and XIP for different algorithm. Then we create a coprocessor version and compare it with the first version. And then we add the third variant, which is the tightly coupled approach. And again, compare it with all the other different approaches. And thanks to these studies, all the different results and techniques that we have applied has been applied to other applications or to other algorithms of the PQC standardization process. In particular, one of the examples is TIRCA, that is a tightly coupled accelerator that has been developed during my internship at CA, which achieves speed ups up to 21 times with respect to the original software implementation for code-based cryptography. So what are the takeaways? To wrap up, I think there are 3 main points of my thesis, which are the effectiveness of CXXVIII tool to deployment this kind of accelerator, the central role that RISC-V has in nowadays architecture design, especially for open hardware one, and the urgent global need that we have for PQC deployment before 2030. So the next step for us is trying to develop a dedicated PQC EECE extension similar to what has already been done for the classical cryptographic algorithm. Because I think that RISC-V together with PQC can actually shape the security of the IoT of the next generation. So thank you for your attention. And if you're interested, here there are all the repository open source of the work that I have presented in this video. Thank you.